Hello there, geometers. This is, well, obviously a geometry video. It is chapter 10, section 7, and today we're going to be discussing special segments in a circle. And so to get started, we have some vocab for you. Segments intersecting inside a circle. When two chords intersect inside a circle, each chord is divided into two segments, which we call chord segments. So here you see the chord that goes from E to D and the chord that goes from A to C, and since they're intersecting inside the circle, you have what we call chord segments. So this red portion is a chord segment, the blue portion is a chord segment, green portion is a chord segment, and the purple portion is a chord segment. So now that we know that we're talking about chord segments, then we can go to Theorem 10.15, which is if two chords intersect in a circle, then the products of the lengths of the chord segment, which is of course why you have to know what a chord segment is, so the products of the lengths of the chord segments are equal. So that's to say that this chord segment times this chord segment would be equal to this chord segment times that chord segment, or basically AB times BC equals DB times BE. So we're going to go ahead and do our first example here. And we have these chord segments. We have a 5 and a 12. So that means that we're going to get, let's see, 5 times 12. And then over here on this chord segment we have 10 and x. So 10 times x would just be 10x. Well, we know that 5 times 12 is actually 60. Divide both sides by 10, and lo and behold, we get that x equals 6, or in your language, 6. All right, so in part B, we have a little bit more of a doozy because we have more variables going on, but we still want to take chord segments times chord segments, so we're going to go x plus 1 times x plus 8. Which is this segment and that segment. We're going to go x times x plus 10. And when we do this, we're going to appear to get a quadratic, but have no fear. Even though we can deal with quadratics, in this particular case, we're not going to have to. If you recall from Algebra 1, when we have two binomials like this, you can FOIL. So that would be first times first is x squared. Outside times outside is 8x. Inside times inside is just x, and last times last is 8. On the right-hand side, we have x times x is x squared, and x times 10 is 10x. And although this might seem to be a big doozy, when you attempt to put the x squareds together on the same side, they'll actually cancel because you have x squared on both sides. And that's why I was saying earlier that it's not going to be actually as hard as it looks. 8x plus 1x is 9x. And over here we have 10x. So we want to move these 9x's to the other side. And we get that x equals 8. Alrighty, so that's how you do example 1. So now we're going to have you, try to get out of the way there if you wanted to copy that down. We're going to go to our first do-it-yourself question here. See if it'll close from here. That's do-it-yourself number 1. And then we're going to go to example 2, which is using the same theorem, but in a little bit of a different way. So here it says, example 2, the true shape of a rainbow is a complete circle. See, that's something I didn't know. And now you know as well, if you didn't already. The true shape of a rainbow is actually a complete circle. However, we see only the arc of the circle that appears above Earth's horizon. So it's kind of have a diagram here of what that's like. This circle would keep going, right? What is the radius of the circle containing the arc of the rainbow? So you kind of only have a portion of the circle being shown here. So you kind of have the circle that's going to keep on going. But what you do know is that this segment here is 0.7, and that the distance from this end point of the chord to this end point is 5. So basically, this chord is actually 5 miles long. And since we had learned in a previous lesson that when you have a chord that is perpendicular right, to the radius, then you're going to be the perpendicular bisector. That tells us that this is 2.5 and that's 2.5. And so what I have here is, in the next slide, a more accurate description of kind of what's happening. So here you can actually put the same thing, just in a smaller version. We have the full circle, and the rainbow is only going from A, D to C. That's the rainbow. And so we have this distance here is 0.7, and then we have the 2.5 and the 2.5. So using that, we can actually solve this little guy. And you're going to want to do something similar with the do-it-yourself question, so make sure that, that you can do that. So what we're going to say here is that we know that 0.7 times the distance from B to E, because remember we're talking about chord segments. So the chord segments here would be this top portion, would be the first part of the chord, and then from here to the other end would be from B all the way to E. That would be the second chord segment. And then on the other chord, you have 2.5 times 2.5, or basically 2.5 squared. So here you're going to divide by 0.7, and it turns out that BE is equal to 6.25, which is 2.5 squared, divided by 0.7, which is actually 8.9. So now we know the distance from B all the way to E is 8.9, but remember, they asked us for the radius. So the radius is actually half of the diameter. So right now what I could do is, if I take from D all the way to E and divide it by 2, that's the radius, right? So what I'm going to do is, I know that DE plus, DB, so from D to B plus B to E is going to equal the diameter. And I know that DB is 0.7, so that'll be from all the way from D to E. So the entire diameter will be DE. So DB, we know from the diagram, is 0.7. We just figured out in this section here that BE is 8.9. So it turns out the diameter, DE, is 8.9 plus 0.7, which is 9.6. And that will be the entire diameter. But to get the radius, we want to divide that diameter by 2. So the radius, which is actually just DF or FE, so I'm just going to call it DF here, is equal half of 9.6, which is 4.8 miles, because our units were in miles, right? 0.7 miles. So that would be my radius. All right, so the challenge for you is going to be that you can create your diagram somewhat like this for do-it-yourself number 2. And I will leave you to it. This is the example or the question, and then we're going to go to our next theorem. And here we have our next theorem, and it's about segments that are intersecting outside of a circle. So a secant segment is a segment of a secant line that has exactly one endpoint on the circle. So in this figure, segment AC, segment AB, and segment AE and AD are what we call secant segments. Okay, so the secant is the part of the secant line. So this is the secant line is the entire line, right? It's the portion of the secant line that has exactly one endpoint on the circle. So from the point A here, it's not on the circle, but B is. And so then, same thing here, D is on the circle. And so then we have that AC and AB and AE and AD are what we call secant segments, okay? So now that we know that, we want to talk about the external secant segment versus just the regular secant segment, just so we can make sense of the diagram, of the theorem, even though you can probably figure this out just by looking at the diagram. But it says a secant segment that lies in the exterior of the circle, so those would be AB and AD, is called an external secant segment. So again, in the figure, AB and AD are external secant segments. They're secant segments that are outside of the circle, hence why it's called external. A special relationship exists among secants and external secant segments, and here is that relationship. If two secants intersect in the exterior of the circle, okay, so here they are intersecting, then the product of the measures of one secant segment and its external secant segment. So here's the secant segment is the entire thing, and its external secant segment is just AB. So you can see here the example AC times AB. So AC is the entire secant segment, and then AB is only the portion that is outside of it. Okay, so that's going to equal the other entire secant segment, which is AE, times just the external portion of it. So here we have then the product of the measures of one secant segment and its external secant segment is equal to the product of the measures of the other secant and its external secant segment. So hopefully I didn't lose you with all of that verbiage, but hopefully you can just base it off of the formula here. You have the entire secant segment times the external part equals the entire secant segment times the external part. So hopefully that's what you can take away from this, because we're going to use that in our next example. And it's important that you be careful that you set up the problems correctly. So remember that what we said earlier, you want to take the entire secant segment. So in this case, it would be, I'm sorry, I'm already doing the do-it-yourself. We want to go to the example. It would be the entire secant segment, which is x plus 8, and then times it by only the external portion, so times the 8. And then we're going to take 10 plus 6, and again multiply that by only the external portion, which is 6. So over here we're going to get 8x plus 64. Over here we have 10 plus 6, which is 16, and 16 times 6, which is 96. Some simple algebra here. We subtract 64 from both sides. Leaves us with 8x equal to 32. And when you divide both sides by 8, we get that our answer is x equals 4. So it's just important that, for example, you didn't put x plus 8 times x. It has to be the entire secant segment times the external portion, entire secant segment times the external portion. So you're going to go ahead and do it yourself number 3. And then we'll go to our last theorem and our last example. All right, so here we have another similar theorem. It says an equation similar to the one in theorem 10.16 can be used when you have a secant and a tangent. So this one is different because instead of having two secants, you have a secant, which is Jm, and a tangent, which is Jk, that are intersecting outside of the circle. So in this case, we call Jk the tangent segment, okay? So the tangent segment is the segment of the tangent with one endpoint on the circle. So basically, in this case, Jk. All right, so the theorem says, if a tangent and a secant intersect in the exterior of a circle, then the square of the measure of the tangent, so that's the Jk part, the square of it, so Jk squared, is equal to the product of the measures of the secant and its external secant segment. So the secant again being Jm and the external portion being Jl. So that's why you have this little formula here. So we're going to use that in our last example here, example 4. Okay, so in example 4 it says PQ is tangent to the circle. Find x round to the nearest tenth. So we are going to set up our tangent segment is the 8. So we're going to have 8 squared. And then we're going to have the product of the entire secant segment, which is x plus 7. And then we want to multiply that by the portion of the secant segment that is outside, which is the x. Which brings us to 64 equals x squared plus 7x. And as I said earlier, in this case, you can't really avoid the fact that you have a quadratic. You don't have x squared on both sides, so you can't just cancel them. I'm going to move the 64 to the other side and make it negative, and then we're going to make it equal 0. And again, remember from Algebra 1, you can try to factor this if you'd like, but I actually already tried that and it didn't actually factor. So what you need to do, if it can factor, then obviously that's the way to go. But if you can't factor, then don't forget that we have our trusty little quadratic formula. And if you recall, I'll just put that over here. The quadratic formula was if you have ax squared plus bx plus c equals 0, so you have your a, your b, and your c. If you have those a quadratic with those three variables in there, then the formula for the quadratic formula was x equals negative b plus or minus radical b squared minus 4ac all divided by 2a. Yes, you remember that song? It kind of brought back memories, didn't it? So using that little guy, we're actually going to solve this because I have that a in this case equals 1, b in this case is 7, and c in this case is negative 64. So using those values, I'm going to plug it into my quadratic formula and get negative b, so it's going to be x equals negative 7 plus or minus the square root of b squared, so 7 squared, which is 49, minus 4 times a, which is 1, times c, which is negative 64, all divided by 2 times a, but in this case a is 1, so all divided by 2. So here I can see that this is a negative 4 times 1 times negative, so these two negatives are going to make it a positive. So really it's 49 plus 4 times 64. And so I'm going to actually end up with 305. If you don't believe me, you can put it in your calculator and you shall see. So I get negative 7 plus or minus the square root of 305 divided by 2. And if I put that in the calculator, I get two solutions. Negative 7 plus the square root of 305 and then divided by 2 is either 5.2, or if you take negative 7 and subtract the square root of 305 and then divide by 2, you get negative 12.2. But we're not talking about lengths here, and we don't want to deal with negative lengths. So at this point, we decide that the 5.2 is the length that makes sense, not the negative length. So we eliminate the possibility for the negative 12.2, and we stick with 5.2 as our answer. So that is how you do example 4. And so I am going to now put your do-it-yourself number 4 question up here for you to do. And once you have completed this do-it-yourself question, you will have completed your notes for this lesson. And I will see you in class, and thanks for watching.